Morning. So you've heard this spiel before, but please feel free to use your smartphones to tweet to the hashtag DonnerDoom, but keep them on silent so we don't have interruptions from those. I'm pleased to introduce Dr. Gerhard Klimeck. Dr. Klimeck is a professor of electrical and computer engineering at Purdue, as well as the director of the Network for Computational Nanotechnology and the Riley Director of the Center for Predictive Materials and Devices. His research interests include nanoelectronic device analysis and development, high-performance computing, and engineering tool development. Today, he will present a talk titled Mythbusting Nanotechnology Knowledge Transfer Through Novel Cyberinfrastructure. Please join me in welcoming Dr. Klimeck.
Thank you. Thank you. So thanks for letting me give a presentation about something we've been working on for some 12, 13 years. I'm going to talk about cyberinfrastructure. So that's an infrastructure based on computing. The incarnation, the special thing here is NanoHub. And I'd like to introduce NanoHub by an animation of global usage sometime in January of this year. You can see day and night go by. You can see people registering. The bigger the symbol, the more people from a specific time and place. And then they turn into simulation users so they can run simulations without installing anything. So it's like cloud computing, but for an end user. And we have about 13,000 users like that, those yellow dots. And then we also started having lectures, seminars, and tutorials on the site. And there's about 300,000. So 20 times more people are looking at seminars and lectures. And it's kind of interesting to look at this animation, but there's also a global view. I'll show that in a second. But the key element of this presentation, what I'd like to highlight today, is really that our goal is really knowledge transfer from one group of people to another group of people. So really being impactful and transformative. And just to make it fun, I'm going to talk about all the things that we were told we couldn't be doing, and I'll call it myth busting. So going through the stuff that were challenges and trying to highlight them, and that they're really myths and that there's many things you can do. So here's a global map of 1 year usage. So basically, nanotechnology and usage on NanoHub is a global phenomenon. Basically, where there's a civilization that has enough energy to light up the night sky, we have NanoHub users interested in technology like this. And I would like to connect today the messages of connecting research and education, that we are collaborative and that it's a global impact. Those are the key messages, and I hope that they can be transferred into a bigger scheme of a view as well. And I want to show that with real data. Like, these are not hypotheses of what could be happening, but all of the stuff that I will be showing are real data. And I guess the punchline is that we are taking actions. We look at our data. We use them to analyze what people do. And just to give you an example, when we made our site interactive, where our tools became interactive, we started to grow from just 1,000 users. We started growing very strongly to over 13,000 users. So usability, interactivity, utility to users is going to be a key element for what I want to talk about. And to me, this is the essence of a research university. That is what we're challenged to do, and that's what we should be doing, being transformative and enabling research and education to collaborate and to be global. So I want to frame all of that, though, in a much bigger context. I want to use NanoHub as an example of how you can address some of the critical issues in society. And I want to frame it in terms of the education impact on society, technical developments, and a growing technology market. And we're missing enough engineers to actually fill that market. I want to talk a little bit about education costs and maybe how an infrastructure like that can reduce the education cost. I want to talk a little bit about stale education and how this infrastructure can make it more lively. And I want to talk about faculty incentives of why we should be doing some of these things. So these are more global issues. And then in the specific sense, I want to talk about enabling research by others, education for others, coupling, as I mentioned before. So I use this sort of as an outline of my presentation, and you see those major points coming along. All right, obviously I don't do all this work myself. It's done by many people. So in this presentation, I almost have nothing of my research group that I will be showing, but I have a pretty big research group here at Purdue that provides content to a certain degree into NanoHub. Then there's a NanoHub and a Hub Zero team. Those are professionals that help operate the site, operate the infrastructure, continue to develop it, keep it fresh, keep it alive. But there's a third stakeholder group, really. Those are the NanoHub contributors, the people that actually put the content into NanoHub. And without them, I couldn't be showing any of these results because the site would be empty. So there's really three stakeholders in terms of contributions to these content authors as well. So it's really a work of many, many people. So obviously, societies have recognized education for many years. And if you look at these pictures, you kind of feel like not a whole lot of things have happened, right? I mean, the format of it hasn't changed. Maybe the size of lectures hasn't changed. And I want to address some of these issues. But we do recognize that education has a financial upside. So here's some data from the Department of Education that charts the median weekly earnings in 2011 as a function of the degree you have obtained. So less than a high school, starting down here at $450 a week, going up to professional degrees that are outdoing the PhDs. So there's a financial upside. So apparently in our society it is worthwhile to get education. There's also a stability downside if you don't have it. If you look at unemployment numbers, those are staggeringly high when you don't have an education, versus people that are highly qualified are changing jobs, and there's a few people that are really unemployed. So our society seems to value education, certainly. There's another way of looking at similar data. So if you take all of the US population and sort them by income and put them into 5 buckets, and each bucket is same number of people, so you put them into 5 distributions, then you end up with a distribution of 0 to $20,000 median income, 20 to 40 roughly, 40 to 60, 60 to 100, and above 100. And interestingly enough, these buckets have the same number of people in it. So now the question is, to me at least, and to many people, when I grew up in Germany in a post-World War area, and I remember my parents distinctively always saying, I want our child, our son, to have it better than we had it. So the question now is, what is the upward mobility? What if you're born into this group here of income, the 4th quintile? What are your chances in the next generation that the child goes up, down, or stays in the same income bracket? Is there an upward mobility? And the one way to look at that is if nothing would change, if we were all the same and completely random, you would expect some 30%. Each of these buckets, you either go down, you stay, or you go up, right? 33% would be roughly what, if there's no influence on that. All right, so if you compare that to people that don't have a college degree, and this is data from the, again, Department of Education, they're 43% likely to move down in an income bracket. So we're looking at the 3 middle brackets here, and if you don't have a college degree, when you come from these 3 brackets in the middle here, your likelihood of moving down is 43%. And if you have a college degree, it's going up by 55%. So those are interesting numbers to see that there is actually an upward mobility afforded by getting an education. But there's also some other interesting numbers that there's 26% on either side of these with or without college that are unaffected. Seems like it doesn't matter whether those people went to college or not, they stay in the same income bracket. And what's kind of sad is that even people that go to college, 19% end up being in the lower bracket than what you started out with. And that sort of shows that there's room for improvement, right? There's ways to look at this that you say, a college degree doesn't serve all the people quite right in terms of that metric at any rate. All right, so here are the full numbers, but I kind of walked you through these distributions. So there's other ways to look at that as well. Higher education is essential for upward mobility. If you look at college graduates by ethnic distribution, you can really see that Asians have, in the United States, emphasized very strongly college education, and their median household income is significantly higher than for ethnically white or Hispanic or black. So we have also social issues that go along, right? On which social groups do go to college and benefit from it. That going to college is starting to become pretty expensive. If we look back to 1965, public tuition basically doubled over the last 40 years or so. Private universities tripled roughly. And if you compare that now to an inflation-adjusted increase, so if you just look at inflation, so roughly the family income has been flat, but public universities went up by 150% and private universities by 250%. So it's getting to be more and more expensive, and that shows in the debt that people have when they come from college. So today, 2015, is the most ever indebted college graduate class. So the median debt is $35,000, and it has been growing, and even under inflation adjustment, it has been growing significantly. So these are, again, data taken from various sources. So this one is from the Wall Street Journal. On the other hand, we have seen other improvements or developments of increase, right? So this is a picture of a pretty famous computer, Cray 2, 1985. That was the world's fastest supercomputer. Cost about $20–30 million. And you have one of those in your pocket or in your purse right now. The compute power of an iPad 2 is about the same as a Cray 2. I mean, that is the technology development we have enjoyed. And these are fascinating machines. And the demand for these products has grown dramatically. The semiconductor market is around $300 billion now. That's a significant market in the world. And the US is actually a technology leader. So the largest semiconductor company is Intel at $47 billion market capitalization. Then we have Samsung. TSMC is a foundry. They don't sell products as such. They deliver products to companies that don't make these products, so that you send them a design. So that's a significant portion. Then US, Qualcomm, and Micron again. So these are very large employers in the United States as well, and they are also looking for employees. So how do we get them, right? To put this into the perspective of a GDP, gross domestic product, we have about 4% of the GDP in the United States is semiconductors. It's a large, large impact on our economy. And in China, it's even more significant, 20%. So if you compare that now on how do we get innovation started, how do we get new people into the system, you start to look at R&D spending, research and development spending. How do we fill that pipeline? How do we do research? So basically, Japan has been flat in terms of 3% of its R&D expenditures. The US has been more or less flat. And you see it, South Korea and China are growing significantly their expenses in that area. And that goes along with the technology development, where we need to have people that actually understand this technology, that can derive it, can drive it, and can forward it further. And you ask yourself, where are these graduates coming from? Where are they being trained? And if you look at that, right now, about 50% of the world's college graduates will come from China and India. So it's a huge number and increasing still. The United States is actually on a negative trend. Germany is down here also on a negative 2% of the world's engineers are Germans. United States, 8%. That's the creation number of new engineers. So that's somewhat of a problem, and it's especially a problem in the US because only about 20%, less than 20% of the US college graduates work in science, technology, and engineering and math. That means 80% of our graduates do humanities or service or banking or things like that. or medicine, but only 20% are working really in creating new products, creating innovation that will create new products. So if you now compare that to another very staggering number is who are we training in the United States? We have foreign students are about 11% or 12% of all doctoral degrees. Seems like an okay number. But backwards I said. All right, but out of those 11% of total graduates, over 50% are getting training in engineering, computer and information sciences, mathematics, statistics, engineering and related fields. So the foreigners that are being trained in the United States, I'm one of them, right, are by and large in engineering. So we have a foundational knowledge. We are on the forefront of training them into the new technologies, but it's often that we send those people back because they don't have a green card yet to stay. So we have policy problems. All right. Alongside that, we are suffering at a state university that the state funding keeps going down and the tuition keeps going up in order to run places like Purdue. All right, so there's been a lot of talk about MOOCs, massively online open courseware, where people train online rather than the older style brick and mortar. Another problem here we see is that the traditional printed textbooks are usually years out of date and they take a long time to update. There's some articles that I'm referring to here on Radar at O'Reilly as a publisher that states it's typically a 7-year adoption cycle. That's not even writing the book. It's just if it's ready to adopt it someplace, right? And writing the book by itself takes another 4 years. So you're 11 years behind the curve if you adopt somebody else's book, unless you develop your own. All right, so there seems to be something going wrong with this process, and here's an example of that these printed textbooks are outdated before they are even published, right? So there's a problem out there, and often we think of it as a technology problem only, so e-readers are starting to take ground, but really the question is who creates this content? Where does this content come from, right? It's professors that are working in research areas. The question now is, can you make their life easier in terms of making these new content items available? And then there's discussions now, should tenure be abolished? Because we are, as faculty members, mostly working on research. We're just creating research papers. But can you actually turn these research papers into something useful to others is a question that would then advance education. So here's one article that starts to talk about tenure being a problem. And here, this is a Nobel laureate. I'm not sure if you're familiar with his image. Peter Higgs. There was a lot of talk about the Higgs boson. This person has maybe published in his career only a few papers, right? But his foundational contribution to science 30 years ago or so was the hypothesis of the Higgs boson. And he says that he would probably not be viable in today's academic economy because he's not turning out papers enough, right? So it's actually starting to be a problem that it's not just quality of work, it's the quantity that's being created. So that being said, there seems to be a lot of issues in education, right? It's important, but it's expensive, it's sort of stale, and faculty members have little incentive to completely innovate because they're measured on something else. So we have problems. And what NanoHub can maybe exemplify that there are some solutions where we do translational work, where we enable research by others, we deliver faculty incentives, we create education for others, we couple research and education, we try to build a community, and then try to translate that into other fields. So that's sort of the setting behind NanoHub in a sense. And maybe this is not so familiar with you, but if you have some faculty members here in the audience, they will identify with this. I mean, I work with my students here in a research team My group builds modeling and simulation tools. There's other groups that do experiments. There's other groups that do theory, pencil, paper theory, or foundational insight. And we create things like simulation tools, or maybe instruments, or maybe data. Right? That's the immediate outcome of the work. And so it's information and tools. And then we might convert that into sort of a seminar that starts to make this in a kind of a publishable form. And once you can present it to your peers, you can probably put this into a paper and create IP or publish it, right? So you move from your research team to some sort of knowledge. And then you publish this, and your customers are your peers, right, that read those papers. And those are typically also on a different planet compared to the normal planet. And so they're in their own silo. Right? So if you do this a lot, you might create a course. And you play with that course on a local level, right? So you start to affect your local students. If you are doing that successful for a while, you will create a textbook, which will be like 4 or 5 years process. Then you will begin to affect the remote students, right? That are also still specialized. And all of us have, if you're a faculty member, we have a web page. If you ever looked at a faculty member's web page, it's utterly outdated. It goes back to the 5 years when they arrived on campus, right, or the 10 years. And when there was a promotion, they kind of updated it and put the latest papers on it, and then it becomes stale again for 5 or 6 years, right? These things are utterly stale. And they're stale because they're really not connected to our core business. They are sort of a sidetrack. Our core business is doing this, and it's not putting stuff on the web. So we don't have a reason to keep the web page updated, right? Because there's no incentive, right? We're all busy. So the question now is, can you change some of that? So the NanoHub solution is that we actually embed or allow people to publish their simulation tools or their data and their recent seminars and their new courses in a web page. And that is the more immediate outcome. It's the closer connection to research that allows people to utilize this material. And then you don't have to keep that web page up to date. It's really the recent stuff is on NanoHub. And that's what you're referring to. So, and then people come to us. That's really a key element of having fresh and exciting material here. People will want to see it. And that is part of the element of NanoHub, and enabling this really long stovepipe to be more directed towards consumers. All right. So here's a picture of NanoHub, but it's much more than a website. So I have a little bit of an animation here. These are visualizations anybody can do on NanoHub. These are quantum dots. These are some impurities. This is DNA strand. You can explore a variety of things where you can put in a search topic and dig down and dive into online presentations on your material that you want to watch. You can search within these presentations. A key element is this online simulations. It's cloud computing. So with a click of a button, you can launch a tool that runs here somewhere in the cloud and then visualize your results. They can be very thin tools, very fast, or this tool actually will run for a couple of hours on a supercomputer, this one here at Purdue, here at RCAC, but we are connected to cloud computing and supercomputing. It's completely transparent to the user. They don't even have an account on this machine. We have an effort on this NanoHub U where we have really a MOOC-like environment with testing on recent courses. So there's some 15, 20 courses in NanoHub U, and then we have over 100 traditional courses on NanoHub already. We foster participation. We try to let people write reviews, sort of a Web 2.0 environment. You can earn a virtual currency for contributing. So hopefully down the line, you can maybe buy faster computing or more storage with this virtual currency, and try to foster community building. And part of that is also foster contribution from the community. So there's a full formal process of contributing to the site. We're getting into data representations and not letting only simulation tools be uploaded, but also experimental data, etc. So these are rather interactive. and you can view over your data and highlight it and share your data within groups. We have a sort of a project environment which you can use for project management to give tasks to people and to share and work within a group. And then we spend a lot of time on impact, on trying to analyze where these tools are used and where these seminars are used and what the impact is. And then every author gets sort of an impact chart. I don't know who this guy is. But the key element here is really that we have hundreds of simulation tools now. We have literally thousands of seminars that are on that site that are being utilized by many people. So I always get the question, so here's the answer. Yes, it's free. We do not ask for funding, or we are funded by the National Science Foundation on a 10 plus 10 year grant. I'll talk a little bit about this in a minute. And I want to now highlight some of the impact stories that we have achieved and what I think is possible in the future. But before I talk about the future, I'll talk about the past. The year 1965 is actually incredibly important, especially to me because I was born. But there was a person that sketched this into his notebook. And it's harder to read here. So number of components per integrated circuit versus relative manufacturing cost per component on a log scale. So what that means is you can make more and more for less and less cost as you go from 1962 to 1965 to 1970. What that means is really what we call today Moore's Law. It was Gordon Moore, one of the co-founders of Intel, who sketched that into his notebook. And you might be familiar with Moore's Law in more this form, where we sketch the number of transistors as a function of years. And on a log scale here for the number of transistors, it looks like a linear plot. That means the number of transistors is growing exponentially as a function of years. So today we have over 2 billion transistors on a chip. So on this Mac over there, Intel chip in there, 2 billion transistors. That's a third of the world population working together without having a war. That is how big that number is, right? It's a complete engineering feat of integration. You might have seen Moore's Law also in this form here. We're making things smaller and smaller, and I love to show the 2004 slide because we can go back now and see how well they predicted it's going to be. And we have reached now device sizes of tens of nanometers. So you might have heard those. If you're an electrical engineer, you might have heard of these simulation tools, Berkeley Spice and Stanford Supreme. This is a circuit simulation tool. This is a process simulation tool. What this thing does is it allows you to create cooking recipes on how to process semiconductors to build these kind of structures, how to etch, how to implant, right? But it's a software that allows you to basically optimize your process. And Spice allows you to put things together into circuits and model it. So all of these things are actually built on the computer before anybody ever goes in the lab, which is a kind of a cool thing. All right, so you might say, that's fine, that's interesting. And I'll challenge you to understand now where these come from. And I don't mean Berkeley/Stanford. That's pretty obvious. No, Berkeley Spice started as a teaching tool between a single faculty member and a student. It was an exercise for a student to model circuits. And it was one of the first public domain codes. Peterson, the prof, carried tapes along, right? This was pre-internet. So he would give a talk like I am today and say, well, we're building this software, chances are there's bugs in it, try it out anyways, and let me know when it doesn't work, because then we can fix it. It was a community effort. It was the first public domain code. And then ultimately students took it along to industry and academia to procreate this material and usage. Stanford Supreme, similar, but it was focused more on the research side, but also public domain. They have community workshops. They engaged the community to try to make it better. And again, students took it along to industry and academia. And ultimately, those two tools are now in any professional design environment that deals with circuits and devices. So I would claim that process simulation and circuit simulation were the key elements to achieve roughly a $300 billion industry. And they came out of academia, out of small groups in academia. So this is an example, two examples of critical development that come out of research, come out of academia, and have huge impact. Now the question is, can you do something similar? Can you do this in nano, where we deal with nanoscale structures and billions of them, and work in them, and really make this research that we do at the university, make it useful to others? That is a key element. That's the key question. And put it into the hands of people. Because this cornucopia here is filled in the United States with an investment of $2 billion each year. Worldwide, it's about $8 billion. There ought to be a way to harvest what is coming out of this research and make it useful. So that's the challenge. That is what we want to do, and that's why we have created this NanoHub. So for you, maybe nanotechnology is people working in bunny suits, like maybe working in chips. Maybe nanotechnology means to you expensive facilities like the Berg facility we have here at Purdue. And those are, of course, experimental facilities, right? Here are models, like here are carbon nanotubes, a visualization that you can do on NanoHub. Here's another animation of quantum dots. These are like artificial atoms that you can build. But these are computational objects, right? And these computational objects actually live in computers. They're not real, right? They're computational models. And they're operated by geeks like me. And you might be aware that there's a huge chasm between the experiment and the theory, right? And what you really want to achieve is collaboration. And what you really want is that the experimentalists really start to use these models to help their own experimental research. That's a huge challenge you want to overcome. And what that means is we, the geeks on the computer side, would have to put that stuff on the web somehow and make it available and usable. And maybe many of us should do that because we need to vet the process, we want to make sure it's really working and we improve on it, and then maybe many people show up. But there's more barriers, right? There's a barrier, for example, to move that in the classroom. Could you move that same material into a classroom? That is not an a priori positive answer, okay? And then, God forbid, you could have economic impact, right? Have that stuff be useful to develop jobs and make it useful to others. And all of that should be easy to use, no installation, should run in any browser, should be a cloud, and just easy to do, right? Just turnkey. That would be the desired thing. So if you really look at that, you can forget about all the nanos piece, right? This is actually a very common dream. You can put any science in there that does any sort of computing or data analysis, right? Now, this picture here is not specific to nano. Most fields have experimental work, theoretical work they need to teach, and they should be impacting industry by some shape or form. So this is actually a very common dream, and the idea of a portal is been around since about 1998, 1997, but there's only few that really succeeded. And I would claim that NanoHub is really the first computing cloud that really was successful. So the question now is, why is this so hard? Why are most of these instances failing in achieving this dream? And to me, the key element is this process here. I mean, us, the geeks, providing this into the computers, right? And making it available on the web. Because we don't do that. In general, most research codes, software, are written by one user for one user. Very egocentric. I keep telling my students, getting a PhD is the most egocentric thing you can do in your life. And they, in general, do it for themselves, okay? There's hardly any incentive to make it usable. So the code and input deck might be beautifully structured like this, but it means nothing to you. It will mean nothing to anybody to run a tool right away. So I call that user hostile. It's hard to use, and it's almost impossible to use. Now this is user-friendly, and it's a graphical representation of almost the same stuff that you just saw. So now you actually can run a quantum dot simulation without learning this gobbledygook language. So we have found a way to come from user hostile to user friendly. And we do that with a technology we call Rapture. And we have to be developer friendly, so people can put on these interfaces rather rapidly and easily. All right, but there's one more step, right? You got to put that stuff on the web. And for that, we have created this Hub Zero environment, which really is the framework in which we can host these tools and make it accessible without installation to anybody in the world. So these are two key technologies. I won't talk about them in detail at all, but I want you to know underneath we developed a lot of technology to make this happen. All right, so while this has been very hard and many people have not achieved that, there's a bunch of myths that have started to emerge about portals, about what's possible, and they really deal with these three issues. On the user side, people really think you cannot use research codes for education. I mean, I'm giving a review every year. In the summer, we talk with NSF, our reviewers, and for several years, people were convinced that you have to write software specifically for education. Or you must write your own code to do research. You have to know exactly what's in the code to do research in nano. Of course, we know in other fields that's no longer the case. Not everybody builds a chemistry simulation engine anymore, right? So they are established, but nano was that new. People really felt you have to write your own in order to do research, period. And the expression was experimentalists cannot use this stuff. They will never use this stuff because it's just pure theory, and you have to have a theorist run this stuff. On the developer side, people said, well, these interfaces are very hard and too difficult to build. When I wanted to put my own Nemo code into some of the grid platforms, I was told, we would prefer you to rewrite your code in Java. We've spent 5 years writing and optimizing this thing in C. I don't have time or effort to rewrite code and introduce new bugs, right? There's no incentive for doing that. But that was the common practice. And you must rewrite the code to go on the web, or there's no incentive to share them, because I can write papers myself, right? Why should I give my code to somebody? It's like my crown jewel, right? Why would I share it with somebody? And then on the accessibility side, there was no end-to-end Science Cloud possible at the time, and people kept worrying about, can you give enough cycles, computing to all these people that are going to use that? So we'll tackle some of that. Right. One way to look at that in a different way is to say, well, these are customers that actually use this at the end. Researchers don't like to be called suppliers, but in a sense, they supply tools and content into a marketplace where we all meet. So you really have to connect and meet the demands of these three different entities. They all have three different expectations and value systems. And unless you address all three at the same time, you are working on a project that is doomed to failure. If you say, I got a really cool tool, I just want to put it on the web, and you don't care about the market being stable and operational and running, and you don't care about it being user-friendly, you're going to have a website that has a tool on it, but nobody will use it. If you don't use it yourself, why should anybody else use it? Right? Eat your own dog food, right? So there's a lot of compute infrastructures that say, we got cycles. Did I mention we got cycles? Please write a proposal so you can get and use our cycles, right? They have a market, but it's so hard to get into the market that the market is not extremely heavily used, or it's only used by a few people that really know how to write these proposals to get in. So that's one analogy one can have. So now I'm going to talk a little bit about the user-friendly aspect of what we do. So here is a step in the right direction. Here's a gobbledygook input deck, but it's at least on the web, and you can run it. And when you click simulate, you get results you can interactively visualize. Okay? So at least you don't have to install anything, and your results are easily accessible. But you can do better than that. You can turn this gobbledygook into a user-friendly interface that would simulate only MOSFETs. If you don't know what a MOSFET is, that's fine. A particular transistor. So this tool is very general, This is now much more specific, right? But if you compare the user numbers, this tool has 2,700 users some 4 years back, and by this time here, this tool had 900 users. This was created by an undergrad summer intern in about 2 weeks. We did this for a couple of tools, 6 of them, that are wrapped around this industrial strength tool, and we could serve over 6,000 users. So usability is a key element. So compare those numbers. I mean, more users, more runs, right? It's pretty powerful. All right, but I have some other numbers I'd like to share. So these used to be the non-interactive user interfaces we had, like what your bank still has today. You have a form, you fill it out, you click go, and eventually you get a graph that you can't do anything with other than copy and paste, right? You can't zoom in, you can't compare to other data. You would have to download the data first, be a computational person, then you can compare to other things, right? It's non-interactive. And we had this tool called Shred since 2000 or even before, and it had about 8 or 9 users per month, and then a couple of poor suckers took it in a classroom and had to do some homework assignments, and they never came back, right? I mean, it didn't change how they used the tool. And then we converted that into something more interactive, and you basically see a little bit of growth, a significant growth, right? And what's even more staggering is that this code, Shred, was an open source code, meaning, or is an open source code. People can also download the source code. Not all the tools on NanoHub are open source. And these 8 or 9 users also typically ended up downloading the code because the service sucked, right? They ended up just downloading it and just installing it themselves because what they were delivered to them on the web wasn't that good. But once the service was okay, there's not that many people really interested in downloading and installing software if they just want to get their work done. Okay? So this is quite insightful, I think, and we turned the non-interactive user interfaces into interactive ones. It's really important to make usable interfaces to users. So, but what these users really do is we balance usability and capability, right? Simple tools are maybe not that capable as the raw tool, but to really use the raw tool, this race car, you got to have special training. But the last time when you guys rented a car at the airport, I don't think you read the 200-page manual that came with it, right? You were just fine with the usability of a normal car. This is similar. And we've seen this, you have seen this. I distinctively remember when the first iPhone came out, people said, crappy processor, too slow, and not good battery life. My Microsoft phone can do much more. It was the Microsoft phone indeed could do much more. It has more capability, but it was connected to the 200-page manual that you had to read to make it usable. I still have not read a manual for any of my iPhones that I had. The iPad was the same, right? We had these tablet computers all the time, right? 10 years before the iPad came out. But in order to use it, you had to read a manual. Right? Now we have kids at home that are 2, 3 years old. They can do iPads, right? I mean, it's usability that's so key. And that is what happened here on NanoHub. When we made the site usable, we saw significant growth. Not just people that were forced to use it because they had to. All right, so what else is different on NanoHub? Is the developer experience different? So let's look at that. Building user interface is too difficult, must rewrite code. Those are some of the assumptions. And they're true for most other gateways. So many proposals read like this. I have a cool code. I'm a researcher. I want to put it on the web. So I will have to hire a web developer that will translate my code into Java or Perl or PHP. Okay? So I lose ownership. I hand the code over, and it takes typically 2 to 3 years to create a new version of this code, because this is real code, right? This is a real thing. Now, I don't know about you, but I don't know a researcher that sits on their butt for 2 or 3 years. So they start to create their own versions here in this other stovepipe. And they get really mad because that version here doesn't have anything they really care about. And it's really expensive to do that. And it costs about, typical proposals read $500K per tool. And no new research has happened yet. Right? It's just that conversion to take the stuff from him or her, put it on the web, and get something outdated. That is the normal process of creating gateways. All right, so just to give you an estimate, right, for 175 tools in 4 years, you would need $88 million. I can guarantee you that NSF is not willing to give us $88 million to do that. But what we have done is exactly publish these 175 tools in 4 years. But as this process exists, what happens is the customers or users scale back their expectations. They say, well, these are not real research codes, right? Which is true. This is code. The original code that was handed over is old now. It's no longer real research. It's outdated. Maybe to speed this up, you made it more simple. You ended up with a toy application. And certainly you can't do deep research because this is already out of date. Right? This whole process is dead to start with. Because the incentives aren't right. This person is disenfranchised. He had to hand over his code, his baby, to somebody else who's going to muck it up. That's how it's going to be. All right. So it generated a whole set of bad reputations, in a sense, on all these gateways and portals. So NanoHub is a bit different. We publish these tools. We basically eliminate this bottleneck. We eliminate the middleman. We enable researchers, without a rewrite, to put their code on the web, and they retain ownership. They actually own that stuff still, which is the real key element. And we have this Rapture and the HubZero environment that does that. All right, so I want to prove to you now with numbers that this actually works. So here in blue, number of new tools growing nicely, green, active developers growing nicely. And what's also happening is these researchers create new versions, updates to their tools. We have now over 1,400 updates to these tools. You can call that suppliers, product, and product innovation. The stuff is still alive. It's not just a tarball that sits on a web. Good luck, $20 on your forehead if you want to use it. So it is alive, and it's working, and people are working together. So here, each dot is a person that is a contributor to a particular tool. So, and they're connected to other people by working with them. That's what this network chart shows. They come from Purdue. This is Illinois, Northwestern, the original partners of the NanoHub, but the turquoise ones are the interesting ones. Those are the people that come from the outside that we don't have a connection to formally, but informally, of course, we're working with them. So now what I want to show you is how important collaboration can be and how powerful it can be. For each of these dots, I'm going to measure how many lines go away from them. Right? So how many collaborations does a person have? I'm going to chart that against the impact of that person. So I want to chart for how many collaborations do you have and how many users do you serve? Right? It's sort of collaborations versus impact. And sort of, I'm showing first median data, and on a linear scale, you can see it's going up sort of parabolically, at least in the power law, meaning it's not just cumulative. The more you collaborate, the more you impact people. Okay? It's actually so powerful, you have to put this on a log-log scale, and then you see it's a straight line. Now, I said I'm showing median data here in red. So median taken across the number of collaborations. So what I'm going to show you now is a dot for each person developing tools. I'm going to put each person on this chart. So this person here had 9 collaborators and something like 20 users. Okay? Here's another person that had, say, 20 collaborators and 2,000 users. Okay? So the interesting aspect really is now that if you look down here, you're equally likely to be successful and serve 2,000 people or just 10 people if you collaborate with a team of 2. meaning it's really scattered success, right? The curve opens up here at the bottom. Versus if you work up there, you really start to begin to have predictable success. The scatter is very narrow. So to me, this is the old approach, and it's the really promotion and tenure criteria. When we ask a faculty member, what is your key contribution in a, if possible, small number of collaborations? Because then we can really measure how impactful you were. And what that means is you're digging in the noise. Okay? So this is the old promotion and tenure, and to me, when I give this talk to Mitch Daniels, I tell him this is the area of the surviving universities that really foster collaboration, where we really want to work with others and we put value into it. All right, so collaboration is a good thing. What are other incentives? Well, each contributor, so Dragica is the shred author. She served some 11,000 users with her 17 tools. Everybody gets a chart like this. It looks really good in proposals where you can say, I'm actually going to impact people, right, with my new research. They put that in their proposal. She can win proposals better. And since we're old enough, we're starting to write books together on how to use the site and how to do computational electronics. But here's another example of a younger person. This is Sheikh Ahmed. He was a postdoc in my group. When he was at Purdue, he created tools. And just like all professionals, eventually he leaves. And he shows up and goes to Southern Illinois University. And suddenly usage picks up at NanoHub, right? Remember the story I said about Spice and Supreme? Somebody takes along a tool to a new place. That's what Sheikh did. He infused NanoHub into existing classes, built new classes, used it for research, and he got promoted with tenure in 2 years. So that's building faculty incentives to participate, right? And obviously, we have some 380 tools online. Apparently, we're developer friendly. It can be done, okay? It's not that hard to do. So that myth is busted. We have suppliers, we have products. Apparently, the website is accessible. I'll talk a little bit more about that later. But now we have a problem at hand. We don't know what all these people are doing. Because we're always asked, are you doing education or research? What are you? Okay? So in a sense, what we have here, we're dealing with these myths again, that they can't possibly do research, right? Because they don't have their own tool there. Or they can't possibly use this for education either. So we have a matrix, in a sense, a computer system that's running, and we don't know necessarily what people are doing. So we stare at this matrix, and the way we look at that is the following. Here's a user, and she comes one day and uses the green tool, doesn't come back the next day, then she uses the orange tool, then the 5th day, here the green tool, then doesn't come for a couple of days, and then again the green tool, okay? So that's a horizontal stacking like this, and I'm gonna run by the NanoHub matrix for you over time when users show up. So I'm looking back in the history of 2010 and sort of see this matrix run by, and I don't see a whole lot until I start to see some patches like this, some stripes, then some patterns, some bigger patterns, some chunks, some big chunks. And you start to wonder, wow, people seem to behave similarly, right? So then we wrote algorithms that actually analyze that, and we find groups of people like these here that basically show up once and use the yellow tool. And then over time, there's another group that shows up throughout the whole semester. This is spring break. There's another group like this that use 1, 2, 3, 4, 5, 6, 7 different tools. These are classes. We can measure classroom size by people behavior. There's no other infrastructure, cyber infrastructure, that I know does that for education. So we can prove we're used in education. Down here are groups that seem to be completely uncorrelated, and by some other measures, we can identify them as experimental researchers, computational researchers, and then there's a group we know very little about. We call them self-study users. But these groups here are actually, we can positively identify who they are, where they are, but we go more than that. We have now over 1,100 of those clusters or classes, at 185 institutions with 22,000 students. It's a systematic adoption. It's voluntary, it's viral, and I'm going to start to wrap down on, or wind down. So I'm going to look at these researchers here and how do we prove we're being used in research. So the way we are doing this is we're looking at Google Scholar. We find over 1,200 papers that cite NanoHub. Those are all the dots, right? Each dot is a paper. They're linked by over 2,500 authors. So there's a social network evolving around that. We can identify them where they are. So yellow is somehow affiliated with NanoHub. Green, 65%, 64% are outside, which is good. We're serving others. We can identify what they work in terms of nano research or cyber infrastructure. There's now papers in the literature on how to use NanoHub in education, in the scientific literature, in the peer-reviewed And 50% of these papers support experiments. But remember, experimentalists will never touch this, right? So these are now existence proofs. And the first time I showed this, I was told, okay, fine, you can do research. But is it good research? So then we start to look at secondary citations on this network and look at research quality. And if you're an academic, you look at H indices. Right? An H index is how you measure one's impact on papers. Right? You write a paper, you want to have somebody else read it and then cite it, and then you keep track on how many times you cite it. So on a log-log scale, here's a junior faculty member. He has 6 papers that have been cited more than 6 times. That person's H index would be 6. If you look at a member of academy, those people might have written 200, 300 papers. They would typically have 7,000 or more secondary citations, an H index of typically 50. When we started looking at that with NanoHub in 2009, H index was 27. Now the H index is 62. The rule of thumb is if you're N years out of your PhD, your H index is N. So if you have a lifetime achievement of 50, these people are 25 years out of their PhD typically, meaning they have a lifetime achievement, would have an H index of twice the number out of grad school. So NanoHub is now 12 years old. We're at 62. We're really supporting powerful research. I'm going to wind down now. I showed you class use, right? That goes back to tool qualification. I can look at the impact of the tools. I can rank these tools and put them on some scale. I showed you the social network charts of how people use it in research. I can rate these tools on research now, right? And people really do think that these are decoupled. You're either doing research or you're doing education. But if I put all the dots on the same chart and each dot is a tool, you can see many of these tools bridge education and research, which is exactly what we knew already, because we said SPICE was a teaching tool at some point and Supreme was a research tool. And SPICE is now industrial use. Supreme I use to learn about process modeling. So I already knew that picture of either or is wrong. But now we can show data, and we can show data over years where a tool is now born, say going back to 2000. We don't know whether it's a research tool or an educational tool. But the users decide what it is. And we track it over time. And we ultimately see how the tools come in. So NCN was created. Then we began to create Rapture, this framework that allows applications to be built easier. And suddenly much more tools come in. The number of users grow, the number of tools grow. But the key message is you can really see nicely how information flows from research into the educational market and is being used and is being adopted. So I'm starting to run out of time, so I'm going to wrap up and say dual use is critical. To me, this is the essence of a research university. We can now measure time to adoption to market, meaning how long does it take to get a tool to be adopted in a classroom. Typical textbook, 4 years development. We have tools that are adopted within a week, a month. The median time is less than 6 months. We move research into classrooms in less than 6 months, which normally takes some 11 years. I think that's very powerful and very transferable. All right. I'm going to skip over this. The accessibility, we can look at CPU cycles or what we provide. We can manage it. It's fine, no problem. And the next dream we have is actually engaging experimental data and having data on iPads, not just PDFs, but they link back to the tools, to the real data. So then we get to reproducible nanoengineering. You can really get to the data, the tools. We won the new competition. I think sustainability will be maybe like a professional society. And this is transferable. We're visual in a presidential document of 2011 in the Genome Initiative. It really literally highlights NanoHub in a presidential document. And we spun out Hub Zero into, NanoHub into the technology group of Hub Zero. There's some 40 hubs running now. They have over 1.5 million visitors on these sites. It has been Purdue Impact. I hope NanoHub translational work can ultimately affect the big questions that are used to motivate this. And to me, this is really the essence of a research university: to be global, transformative, to grow, to collaborate, to be recognized, to be creative, and to really enable that at a place that is as cool as Purdue and as it has been for me. And with that, I'll thank my family to putting up with me.